All right, so well, welcome everyone. Good morning, and thank you for coming. It is my pleasure today to introduce to you Enrico Masoero, who is coming to us from Cardiff School of Engineering in Cardiff University, which is in Wales, UK. And he's a senior lecturer in the Materials for Life group. So Dr. Masoero received his PhD in structural engineering at the Politecnico di Torino in Italy. His doctoral work, which sounds very interesting, was focused on particle-based simulations of building collapse. So maybe one day he tell us something about that. But after that, after his PhD, he started a postdoc back in 2010. He moved to MIT to do a postdoc where he started studying cement hydration at the molecular and nanoscale. And currently, he uses a suite of multiscale simulation methods. And his focus is on gaining fundamental insight into hemo-mechanical phenomena in cementitious materials. And his research has been published in a broad range of high-profile journals, including PNAS, PRL, etc. So Dr. Masoero is also a member of the Material Properties Committee of the Engineering Mechanics Institute in the American Society of Civil Engineers. And with that, I don't want to take any more of his time for the talk. So please help me welcome Dr. Masoero and Enrico. Thanks for being here, and the floor is yours.
Thank you very much, Luis, and also Pranoy for inviting me for this seminar. And thank you everyone for taking the time to be here today and listen to what I'm gonna say. Thank you also for the fantastic presentation. And I won't add much to it. Just let me open here it is. Just that in 2013, when I went away from the US and back to Europe, I went to Newcastle University. There I spent the first 8 years of my faculty path. And then I moved to Cardiff recently, only this August. So I'm pretty new to Wales. Today, I'm going to talk about modeling and simulation and how this can help, if it can help us design better concrete. Before we go into the modeling bit, though, I will try to convince you that there is some scope for modeling to help in some current challenges that we are facing with concrete production. And my starting point is concrete and sustainability. One of the reasons why I got involved in concrete is that it's a fantastic construction material. It's a construction material that is low cost. We can produce it with a low tech procedure, but this procedure still gives very robust product in the end, which is shapeable. It gains strength rapidly. If well designed, it can be very durable. So it is a fantastic combination of properties. And as a result, we end up producing really lots of it. So we are over 3.5 billion tons per year, and this figure is increasing, probably doubling by 2050. As a result of this huge production, despite the producing 1 kilogram, a unit weight of concrete as a low CO2 process, when you multiply that times 4 billion tons per year, this becomes a huge quantity of CO2. And as a result, currently producing concrete alone accounts for about 8% of global CO2 emissions. And also this is increasing with production. And this is against all the environmental targets that we have been casting for 2050, or you might have heard about this COP26. So all these plans and roadmaps that are trying to decarbonize our society will have to face at some point the fact that concrete production is a big chunk of it and is growing and is increasing. So what can we do to reduce the CO2 impact of concrete production? Well, in this slide, I'm trying to show you what are the main sources of CO2 emissions in concrete production. So this graph here, without going into the details, is telling you that most of the CO2 embodied in concrete actually is embodied in the cement part of it. You can reduce it if you use high percentages of replacement with slag or PFA or other things, but still it's the biggest part of the CO2 associated with concrete is cement. And in this picture here, you see the different stages of cement production and how they contribute to CO2 emissions. And you see that the big players here are the calcination process, which happens in the kiln, and the fuel that are used to fire up the kilns. These are the two big components. So why are we consuming so much CO2 there? Well, a brief introduction. What happens in the kiln is that we mix limestone, so calcium carbonates, with typically clay or shale, so a source of aluminosilicates. And when we shoot this up at high temperatures, you obtain all those components that make concrete a reactive material that we know, cement, the reactive material that we know. So we start obtaining dicalcium silicate, or C2S, tricalcium silicate at higher temperature, as well as the calcium aluminates. But as a result of this process, these are the things that we want, we also get this carbon that was bound to the limestone, it has to go somewhere, and it goes away as CO2. So there is emission that is intrinsic to the chemical reactions taking place in the kiln. This is called the calcination part of it. Of course, to get to these high temperatures, well, you need to use fuels, and fuels also contribute to a large part of CO2 emissions. So these are the two big sources of emissions. So how can we cut down emissions looking ahead in time? Well, the things that we can do immediately is try to switch to different fuels so that they are renewable energy potentially, or biofuels, lower CO2, and also changing the chemistry of the cement in such a way that this calcination process is not so CO2 intensive. Other things we can also do that are maybe not material related, but more asset related. For example, we could try to demolish fewer buildings. So we build less new buildings, and we try fewer new buildings, and we try to instead extend the service life of existing buildings. Or we could design future buildings to have a longer service life, so less material, so make it more durable. So we replace the built environment less often. And also, looking ahead in the future, if we can validate methods that allow to reuse concrete elements instead of demolishing them at the end of life, that can further reduce the production of new concrete and new cement. But these are more things that are, they involve other dimensions beyond the material. But certainly, if we want to get an impact in 30, 40, 50 years, we will have to move towards using less material, as well as making the material and the fuels better. So this graph here shows the roadmap that has been cast by the UK concrete group that is part of the Mineral Product Association, and they are trying to reach net zero emissions by 2050. And without going too much in detail as well here, what this data show you is that pretty much they want to remove all of the emissions that come from transportation and from electricity that is being used in various stages of concrete production. So they want this to be completely carbon-free, typically using electricity from renewable sources. They want to reduce the CO2 from fuel emissions, that big component of cement production, by 40%, and it's mainly moving towards biomass. And finally, they want to reduce the emissions that are intrinsic to the calcination process by about 30%. This is their plan. And the rest, whatever they cannot achieve from these measures, they are planning to use carbon capture and storage. So this is to say that there is work going on in this direction. It's a recognized direction to move for concrete production. If I'm asked to share my vision of how concrete and cement will look like in the future, and this is something that is not just my vision, it is a big part of the community thinks that this is the direction to move. Well, eventually what we want to do to try and reduce as much as possible the CO2 embodied in the material is to move towards more and more blended cementitious materials. So try to put in as much waste, byproducts, industrial byproducts, mineral tailings, anything that you can really use that can be cementitious or can at least contribute positively to the cementitious material but have a low impact, chug it into the concrete. One good thing of cement and concrete is that you can put almost anything into it and it's still kind of gonna work. And if we can do that, we can use local supply chains, which also support circularity of local economies. So it's a positive thing. We can also try to reduce calcium oxide in the formulation. And one example is to move towards alkali activated clays, calcined clays. Potentially those alone could replace Portland production completely over the world. Is the only material that we have available in such a large amount that could completely replace Portland cement today. And alone, this one could cut emissions by 30%. So if on top of that, we put the byproducts, we could go beyond the target of 30% that we saw in the previous slide. So eventually, the idea is to end up with concretes that in 20, 30 years' time will be extremely diverse with different compositions that use local materials, local supply chains, exploit circularity, local minerals. So something that becomes very bespoke and trying to minimize the CO2 embodied in the material. But of course, if we move in that direction, we end up with materials that are very different from one another. We move away from the idea of a standard concrete, standard cement that we know well and can be researched in different parts of the world. The same material made sort of in the same way could be very different and have very different impurities from one region to another within the same country, let alone in the world. So this becomes a challenge from the scientific point of view. And the challenges are, of course, contextual ones, because if we move away from the production of a material that we know today towards new materials, then we need to change the supply chains, the production plans, the standards. So all these things will have to be adapted to this new vast portfolio of new concretes. But also there is the issue of having confidence that these new products, these new concretes can perform to the standard. And one thing is reaching standards for workability, strength, and short-term properties. This is quite easy to do and check. But when we talk about long-term properties, this becomes very difficult because we are casting a new concrete today using a new stream of byproducts, and we don't know how this material is going to behave in 20, 30 years' time. So how can we convince clients, city councils, and producers to switch to a new material without knowing how it will behave in the long term? And this is where, to me, science really can contribute. It's trying to build confidence that these new materials will actually be safe to use and can achieve the standard that we want for durability. So we cannot predict the future. So we are going to move into modeling soon, how we can help creating confidence. I will try to avoid the word predictive, because I don't think that is the right way to frame the discussion. It's more about building confidence, which means understanding the mechanism that drive the degradation, knowing how we can avoid and steer this mechanism by changing the chemistry of the material, for instance, so that it doesn't go into negative degradation mechanisms. Also building some ability to understand when a material is starting to degrade, so the ability to spot when things go wrong, and finally an ability to correct and manage the issues on the fly. So it's not just modeling in the long term, but it's creating mechanistic models that can help us manage concrete during its lifetime. And if we think of how do we get the feeling of being in control when we talk about ordinary concretes, existing concretes, well, we have confidence about their performance because we know the main degradation mechanisms and how they can be coupled. We don't know everything, but we know a good deal. We have a statistics of short, medium, and long-term data. We know how we can diagnose degradation on site, and we have experience on how to fix it. Also, because we know the mechanisms and we have data, we have developed an array and a suite of accelerated aging experiments that try to excite those mechanisms in a shorter time and can give us an idea of how the material will behave over a long time, despite doing a short-term test. And we could, in principle, apply these same experiments to a new concrete. But in this case, we will not know whether the aging experiments are actually activating the same mechanisms that would be activated in the normal degradation, because we don't understand the mechanisms of a new concrete well enough. So pretty much we don't have a method nowadays that can tell us how these materials will behave in the long term. Even accelerated aging experiments cannot be completely trusted. And this is creating a barrier. I know that some concretes are not being adopted in the industry because there is no confidence about their long-term performance. And One difficulty that emerges when we talk about predicting mechanisms and aging of concrete is that concrete is extremely complex. If we just look at the cement paste in this case here at the hundreds of micrometer levels, this is a pictorial, of course, but where you can see that there are many different processes happening together. For example, some grains, some crystallites may be locally under a highly saturated pore solution, so they may try to grow, but by growing, they may impinge on other materials, creating pressure, called crystallization pressure. Other crystals instead may be under pressure, and therefore this may stimulate their dissolution. This is a process called solution pressure. The solution itself has diffusive processes, and there is gradients of concentrations. There can be interfaces between minerals and minerals, minerals and solution and air. Some parts of the structure may be under stress and locally undergo irreversible displacement, like those sustaining creep. There can be overall diffusive processes on larger scales, like heat diffusion or diffusion of chemicals in the macroscopic sample. And overall, the whole thing may be under a heterogeneous state of externally applied stress. So it's an extremely complicated and coupled process. And I'm not even talking about interfacial zones, aggregates, and rebars in this picture. So everything gets even more complicated. So when there are all these coupled phenomena, how can we be sure of what is going to govern the degradation of the material in the long term? But this is where, as I anticipated, modeling could help us a little bit. And models, in order to give us some confidence on mechanisms and management strategies, they must have some properties. First of all, they have to be physical. They have to incorporate physical mechanisms. Database models are a fantastic tool, but when we try to get to extend our predictions, let's call it, I use the word prediction, when we try to extend our models beyond the data that are already available, so for a concrete short-term data, but we want to extend the results of the model to the long term, when we want to go beyond the data set that we use for training, database models can be limited because the extrapolations can be very limited. Whereas if we understand the mechanism that is driving a certain process, even in the short term, we can still consider that the same mechanism can be reliable if we look at how it keeps behaving in the longer term. So having a physical basis is a way to build this confidence. Also embracing the complexity and the coupling. So if we just focus on individual mechanisms like those that I showed you in the previous slide one by one, we may lose some coupling between mechanisms that could be synergistic or could actually hinder some of the phenomena. So we need to account and explore the coupling. Also, we need to focus on the right length scales. And I will tell you more about this, but the typical plan of a multiscale model starting from quantum going up to buildings, it's very challenging and it may be very limited, but it also may be not necessarily what is needed. Depending on the type of degradation that we want to explore, there may be a restricted range of length scales that is worth exploring and that could reduce significantly the complexity and the uncertainty in the model and give more confidence that what we are modeling is meaningful and is not random pretty much. Also, one thing that the models should be able to do is cope with very wide timescales, because some of these processes start from molecular processes that take fractions of seconds, but then they could extend logarithmically in time, even getting to the point that each event can take seconds, hours, days. So we need to have the ability to flexibly maneuver across timescales. So in the case specific of concrete, the range of length scale that I find particularly important is the nanometer to micrometer. And the reason for that is that many processes do take place at those scales. For instance, hydration processes, where cement precipitates and crystals precipitate and dissolve, is typically a microstructural level process. Morphologies are generated in this range scale, complex morphologies and porosity. Phenomena like creep and the stress relaxation that drives creep, they originate at the micrometer length scale. And if we think about crystallization pressure or capillary pressure that caused by self-desiccation, for instance, this is also something that occurs between the nanometers and the hundreds of micrometers length scales. So many of those processes that I showed you in the previous slide, they can be resolved at the nanometer to micrometers mesoscale. So before going into what model I'm using and I'm developing, I just wanted to give you an overview of the existing models at different length scales. So we typically start at the atomistic level with molecular simulations. They are models that couple together chemical and mechanical processes, because chemical reactions are pretty much bonds that physically break or form between particles. So it's all mechanics, but it also captures chemistry. If we go up to the micrometer level tops, we have coarse grain simulations based on interacting particles. And these are traditionally studied for mechanical properties. So the particles are mechanically bound. You can deform, you can stretch, you can extract mechanical properties of your material. At the larger scale of the micrometer to millimeter, there are very popular are microstructural development models. There are a few varies around the world. They are mostly focused on chemical reactions of multiple phases, but they can also be then, the chemical structures can be plugged into a finite element solver to extract mechanical properties. But chemistry and mechanics are not coupled there. You resolve the chemistry and then you plug it into a mechanical solver. Whereas at the macro scale, macro level, you have both discrete and continuum-based models for concrete samples at this scale. And in this case, typically you have both chemical reactions and mechanical processes, but you have to build them in. You have to give them at the constitutive level. So it's a coupling that you get as much coupling as you give it as an input, pretty much. Then there can be diffusive processes. So there is some soft coupling, but it's not that both are predicted or captured in a mechanistic way at this length scale. There are inputs from lower scales. On top of this, there are some interesting models that are thermodynamic and kinetic models. These models are typically analytical. Rarely they are structurally resolved. They are more a set of differential equations that are solved simultaneously. And the advantage of these models is that they are defined based on rate laws at the molecular level, but they can equally well be applied at the macro scale. So they are really scale-free, pretty much, these models, but they don't give you structural information. They give you chemical information, but they contain many interesting processes that we will use later. And phase field models, phase field simulations actually have been used across the length scale between the micrometer and the nanometers and the micrometers, which is the interesting one for concrete aging. They are a powerful tool. They are very advanced for chemical reactions, but the mechanics is still quite basic there, especially when you talk about many different phases with nonlinear mechanics. If you want to plug this on top of chemical complexity, these methods typically are unmanageable with state-of-the-art computers. So let's take a break now. Let's take a breath. This was the context that I wanted to give you to get to the point of why I developed a different type of simulations that is trying to pick different elements from these models here, specifically this model here, this model, phase field, and thermodynamic, and trying to combine them in a way that gives us access to degradation mechanisms in concrete. So the models I have been developing are based on particles, interacting particles, and they are targeted to length scales between tens of nanometers and hundreds of micrometers, pretty much. These models are therefore mesoscale models, and I see them still in the vision that I have. These will be integrated and communicated with larger scale models. And for instance, larger scale models could be used to resolve diffusive processes, heat or chemistry. And then locally, you can have microstructures being resolved with the models I'm going to introduce that give you an idea of how the degradation is evolving in different points of a sample. The inputs for this model are coming from a combination of molecular simulations in some cases, but we take many inputs directly from kinetic modeling and some directly even from the experiments. So that's why I don't consider this a multi-scale model in the sense that there is a pipeline from molecular to meso to macro. It's more the macro scale gives us information about diffusive processes. The mesoscale model gives us the relevant mechanisms, and some of the inputs are taken from a breadth of possible sources that include also molecular modeling, but are not limited to that. So in this model, what you see here is each solid phase is represented by particles of different colors, but also in the background between these particles in the pores, there is an implicit solution that is described as a field of concentration of different ions and water and air. So it gives you an idea of a field of a continuous field that describes the solution in the pores. This system, so both the solution in the pores and the solid, evolves together, trying to minimize its free energy. So it's a coupled system, and this free energy can be relaxed in two ways. There can be chemical transformations that can imply precipitation, dissolution, diffusion, that can lower the free energy of the system, but also mechanical interactions, because these particles are mechanically interacting with each other. So stress relaxation is another mode to minimize the free energy. But this free energy is the same, is the sum of the two contributions. So the two processes, chemical and mechanical, are coupled in the same free energy functional. The particles are typically in the range of 100 nanometers, but then depending on the simulation can be smaller or bigger, but think about this length scale. And okay, and this is what I already said in the previous slide, it's just a repetition. About the mechanical interactions, the simplest way you can think of it is linear springs connecting each pair of neighboring particles, like a harmonic potential with a cutoff. In this case, you would have parameters to describe this interaction, like the interfacial energy that you get when you break the bond, or the stiffness of the bond itself. And these properties can be obtained either from experimental data, or as I'm showing in this video here, it could be a molecular simulation where you create particles, put them at different distance, and then you construct point by point this energy versus distance relationship that gives you the interaction force, and so the bond. For the chemical part, instead, we have here the two main equations that are describing the solid precipitation of new solid and dissolution of existing solid. And I'm not going into the details here. This is a modified version of Eyring equations that are typically in chemical kinetics. But what I have highlighted here are the terms in this equation that account for the free energy. So the free energy that is being minimized by events that are controlled by a given rate. And this free energy features in some terms of these rates. So the rate at which particles will tend to dissolve will depend on this beta, which takes into account the chemical potential. So it tells you pretty much that if a particle is in an undersaturated solution, its free energy will benefit from the particle dissolving, or vice versa. If it is in a saturated solution, it will benefit from the particle precipitating. A term of the free energy is this activation barrier, which is something that has to do with how difficult it is to trigger a chemical reaction. And then there are these terms here. Gamma is the interfacial free energy, so the energy that is stored on the interface of a solid with another solid or with the fluid also features in how likely it is for the particle to dissolve. And then there is this delta U, which is the change in interaction, mechanical free energy. So if you're trying to dissolve a particle that is under stress, this term will be such that the rate of dissolution will become high. So this is how I'm capturing the coupling between mechanics and chemistry, is by plugging free energy terms into rate expressions that tell me how fast different phases precipitate or dissolve. In this model, what I do is that I assume that mechanical equilibration is immediate, it happens immediately, and this is because typically mechanical vibrations are fast compared to chemical reactions. And for the background diffusion, there are diffusive processes in the pore structure, and they are coarse-grained, treating the structure as an effective porous medium. Then in many simulations, I actually consider the diffusion to be infinitely fast as well, but we can also simulate diffusion through the pores of this material. And all of this is implemented into a kinetic Monte Carlo algorithm, where essentially what we do is we try all the possible precipitation or dissolution events that can occur everywhere in the solution. We can also include creep events, rearrangements, mechanical rearrangements. For each event, we compute the change in free energy that event will cause, like precipitating a new particle here will change the free energy of the system by a certain quantity. And we have a list of all the possible events and the rate of each event that we're trying to execute. And we pick one event with the probability that tells us fast events should be picked more frequently. So this is how we create new configurations evolving over time. How do we get the time scale though? Well, the time scale, and that's a strength of the kinetic Monte Carlo method, is proportional, is a result of the simulation, is proportional to the sum of the rate of all the possible events, inverse sum. This means that if you know all the rates of the possible events which depend on the free energy change they induce, then you can get the time, the typical time that it takes for the next event to happen. So if you are in a stage where the structure is evolving rapidly due to fast chemical reactions, then this time will advance by a small quantity at each time. But if you are in a logarithmic regime where the material is aged and reactions start to be very slow, there is no problem. You just sample the next event, simply the time scale associated to this event will be very long. But this is not like a molecular simulation where you have to fix the time step initially. The time step is a result of the technique. So it's not bound, we are not bound to a characteristic time scale. Let's see some results and then let's wrap it up. I will show you three applications that I've already been exploring with this method and show you what kind of results we can obtain with these simulations. First result was published in 2017, where the code was a first draft. But the first problem we tackled was the precipitation of calcium silicate hydrate in cement. This material is the main hydration phase. So to model it, we started with the surface that should represent the surface, a fraction of the surface of a particle of tricalcium silicate, which is one of the main reactant phases. And we wanted new particles with an implicit solution in contact to it, containing calcium and silicon. And we wanted particles of calcium silicate hydrate to form in this solution and precipitate on the surface to simulate the process of growth of new phases. And we know that this process should give us a trend that is accelerating initially, forget about the first peak for now, but it's initially accelerating over a few hours and then decelerating. So we should be able to simulate about 24 hours to give a meaningful result. So to do that, we treated the CSH as an agglomeration of particles of 10 nanometers each, so containing thousands of molecules. So we adapted the rate equations I showed you before. They were only for single molecular reactions. So we put a sum over all the molecules in a particle, pretty much. So we coarse-grained the rates. And then we ran the simulation and we saw that the type of mechanism that we observed was each blue element here is a CSH nanoparticle. They were aggregating, they were starting to precipitate on the surface, then grow outwards to minimize the interfacial energy as hemispheres. And when they started to impinge one against the other, the rate predicted by the model started to decrease. And we were able to simulate 24 hours of process with this method. We also saw that if we assume that the solution chemistry that is represented by beta, the saturation index is called, was constant during the process, then we would get the acceleration, but then we wouldn't get any deceleration. Whereas if we were considering a typical realistic evolution of the solution chemistry in cement, which is decreasing over time, then we would get an initial acceleration prompted by the aggregation process, so mechanically driven, followed by a deceleration due to this depletion of the ions in solution. So this is an example of how chemistry and mechanics together are determining the evolution of rate and morphology over time. And then we started playing with it a little bit. We considered if the CSH had weaker interactions that we considered in the initial model, then we would get the gel-like structure. If it had stronger interactions, then we would have a perfect coverage, like layered growth on top of the tricalcium silicate. If there was no substrate, we would end up with Avrami-like nucleation and growth. And then if we started playing, what if we had the crystalline substrate and crystalline material forming on it, and then we had this layer by layer perfect growth. And instead, if we put a crystalline material on top of an amorphous substrate, we saw that we would predict initially formation of an amorphous nucleus, but then the crystallization on top of it, and we started to obtain these fancy morphologies. So this is a tool where tweaking the chemistry or tweaking the mechanics, we can explore many different morphologies. The second result I want to show you has to do with the dual process. We saw the precipitation of CSH, but we didn't talk about the dissolution of tricalcium silicate. Well, the second application is recent. We published it last year, and it's about simulating the dissolution of tricalcium silicate crystals. And this is a very interesting problem. If you put a tricalcium silicate crystal in water, if the water is saturated in this near saturation, so there is a high concentration of calcium, especially in it, then the dissolution will be quite slow because there is already many molecules dissolved. But if you start lowering the solution concentration towards pure water, of course, you would expect a faster and faster dissolution rate. So the vertical axis here is the dissolution rate, and the beta is the concentration of the solution. So less and less concentrated, you would expect faster and faster dissolution. But actually what happens in cement is that it starts faster and faster, but then it suddenly accelerates over a certain range of solution saturation. So there is a highly nonlinear sigmoidal dissolution rate curve. And similar curves are observed in many minerals in literature. Earth scientists know this very well, and they have explained it as the activation of certain crystallographic defects where there is a localized stress. So if you think of this defect, for instance, this is a screw dislocation on the surface, this generates a shear stress state. And if you have a highly concentrated solution, this concentration is not high enough to stimulate the dissolution in this defect point. But if you go low enough with the solution concentration, then you are actually able to trigger the free energy change from beta plus the stress relaxation in that spot is enough to stimulate dissolution, and this causes a very fast and exploding dissolution in those sites. So it's stress-induced dissolution. And we said, well, this seems the perfect problem to tackle with our method where we couple together stress and chemistry. So we created a model surface of tricalcium silicate, like you saw in the previous example. In this case, we put one particle is one molecule of tricalcium silicate. We didn't do coarse graining. And then we put an implicit solution where we can control the concentration of it, of calcium. So the beta, saturation index from pure water to a highly concentrated solution towards here. We put interaction properties that are parameterized for typical properties of tricalcium silicates. And then we generated a screw dislocation. So we lifted some particles, we created the ramp, and this is how you create the 3D morphology of a screw dislocation. What is interesting here is that when we distort, when we deform our structure, we do get a local stress because we are stretching the particles, but these local stress are predicted by the model. They are not imposed like you can see in other kinetic Monte Carlo method, because the particles are off lattice, so they can go everywhere. You can relax the stress, the strain energy, and this develops the corresponding stress. The stress that we are predicting from this distortion is consistent with what the literature indicates to be the stress profile near a screw dislocation. And then we started dissolving the system. So when the saturation is high, almost close to equilibrium, then we get a little bit of dissolution around the most stressed point. We do get a little bit of dissolution on this plateau that we have generated, but then it doesn't continue. So it dissolves a little bit slowly, and then it stops. But if we hit a low saturation index, this is what happens instead. You see that this screw dislocation starts to develop these so-called edge pits. The stress gets relaxed around it, and then you have this staircase profile that is being formed, that is a mechanism known theoretically as step wave dissolution. But this is the first time that a model, that a simulation, starts from the screw dislocation configuration and is able to see the opening of the edge pit and the emanation of these step waves of dissolution that eventually peel off the structure. When you activate this is when you get the acceleration of the rate that I showed you before. And then we started looking at why do we get a very sharp transition from essentially zero rate to a finite rate in this simulation. In reality, the experiments show a smoother transition over a range of beta, but then we saw how local properties such as activation energies of surface energies, so impurities, could shift significantly the level of beta where this acceleration occurs. So in a complex material, you can expect to have a complexity of local surface properties that can explain why in the experiment the transition is smooth rather than being very sharp at one level of beta. Finally, I would like to touch on the last application, and I'm conscious that I have 5 minutes. I'll try to be as fast as possible, but this is probably the most interesting one. So I'll try to be fast, but I don't want to overlook it. This is something I'm working on now with a team of researchers, and this is on cement paste carbonation and self-healing. So what you are seeing in this simulation here is a system that, again, each particle here is one molecule, because this is part of a project where we eventually will get to the micrometer, but we are just starting. And what you see here in white are CSH particles, in gray are calcium hydroxide particles. So this is a typical OPC paste, the main phases of it, let's say, calcium-based phases. And what we want to simulate is carbonation. So in blue, there is the water in the pores, and we fix the solution to a pH of 12. We fix a concentration of silicic acid or silicon-based ions in solution. And we also fix the concentration of carbonate, so CO2 if you want, in solution, to be at equilibrium with atmospheric CO2. And if we run the simulation with this code, what we expect is that when there is only water and CO2 in the solution, the calcium hydroxide will dissolve, and releasing calcium in solution, this calcium will reach a saturation level that is high enough to precipitate, to react with the carbonate and form calcium carbonate. And this is what this movie is showing. You see that progressively there is dissolution. Well, you may not see the dissolution of the black phase because it's very limited yet, but you can definitely see the precipitation of the carbonate in the pore space. So we are able to simulate the whole process of carbonation, for now at a very small scale, but we are coarse graining it to larger levels. What kind of results quantitatively can we get out of this model? Well, we can monitor, for instance, the concentration of calcium in solution. Initially, it increases because calcium hydroxide is dissolving, but then it reaches a plateau when the carbonate starts to drink away the calcium that is being released. So when the saturation of the calcium carbonate phase is sufficiently high. One interesting thing to notice here is, well, 22 millimolar is what you expect in a typical OPC solution. The time scale is interesting. We're talking about a simulation that, even if here we are at tens of nanometers length scale, we are able to cover 10 nanoseconds of system evolution. And if you look at individual steps, the first steps really take, the time step that is predicted is in the order of microseconds, but then as the simulation evolves, the steps will be in the order of milliseconds. This is even better shown here. This is the time step during the simulation. Initially, it's very low, but then it reaches the tens of milliseconds. And then towards the end of simulation, each time step is actually even longer. That's because the KMC, the kinetic Monte Carlo, is adapting its time step to the speed of the events that are taking place. It's not imposing the time step. We can also monitor the dissolution rate, of course, of any phase, or precipitation rate of any phase. This is for the calcium hydroxide. And again, it starts dissolving quite fast when there is pure water, essentially. But then when it reaches saturation for precipitation of carbonate, then it starts to be significantly slower. We can also monitor for each solid phase what is the saturation degree, so that saturation index, so any phase that has a saturation index higher than 1 is likely to precipitate. Any phase that is below 1 is likely to dissolve. And this is what controls the fact that hydroxide is dissolving, carbonate is precipitating. We haven't let CSH precipitate. That's why it's not precipitating, but it would a little bit if we could. But then another very interesting aspect is that we can monitor the pressure that is being built into the system over time. And because calcium carbonate, if the saturation index is sufficiently high, the calcium carbonate will want to precipitate, and it can just squeeze into small places where maybe the only way to squeeze in there is to create pressure. And this is exactly what is happening. The pores are tiny in this configuration. So for the carbonate in yellow to fit in, it has to push away the other particles, and therefore it's building up a crystallization pressure, which is also predicted straight from the simulation. So this is the range of results we can obtain. And then very, very rapidly, this is an application to a system that is initially cracked. And because of the carbonate precipitation, it's healing. And then we see an evolution of mechanical properties over time. So we are building up strength, the material is fixing its crack. And we are also applying these to a system that is also featuring bacteria. So the bacteria will eat nutrients in solution, will release CO2, and the CO2 will stimulate the precipitation of calcium carbonate in coupled simulations. And this is really where we are trying to get with all this carbonation business, is to get to these coupled simulations that for now, they produce numbers. We don't know if they are correct. So we are in the validation stage. And this is part of a $1.5 million research project funded in the UK by the EPSRC. So finally, let me conclude. What I've showed you today is we started with the roadmap to reduce emissions from concrete production. We saw how a barrier is that for the implementation of new concretes is that we don't have long-term experimental data on it, and we cannot trust accelerated aging tests blindly. So we need to understand a bit better the mechanisms that would drive the degradation of a material depending on its chemical composition and microstructure. And I indicated that the possible pathway to do that, or to help in doing that, is to combine models at different scales, although not necessarily going for the whole multi-scale picture, but at least minimum level of multi-scale understanding with the specific focus on the mesoscale, where all these coupled mechanisms are likely to concentrate. And in this mesoscale, I've introduced what is out there in the literature. Nothing really can do the whole range of coupled chemomechanical processes as we would like to have. And therefore, I've presented a method that we have been developing between Newcastle and Cardiff in my team over the past 5 years. That are these kinetic Monte Carlo simulations based on chemomechanical rates. I've showed you a few results. I've showed you applications to the dissolution, to the precipitation profile and rate of calcium silicate hydrate in cement, to dissolution, stress-induced dissolution in crystals, again with application to cements, and to the carbonation problem, where I showed you that we can get both chemical informations over time, as well as an insight into the development of crystallization pressure and other mechanical properties. I am working on this model mainly for cement, but there are just a couple of things that I would like to mention. This is the very last slide. All the simulations I've seen so far, there were no diffusive process in the simulation. The solution was only considered as, diffusion was considered to be infinitely fast, so immediately equilibrated. But I've already implemented diffusion for a different problem. This is a problem that I've been working on with Politecnico di Milano in Italy. And what you see here is a lithium, metal lithium electrode in a battery. This is discretized as particles. We put in electrochemical reactions. And what you see here in yellow is the electrolyte. So you can imagine that there is another electrode right here on the right. This electrode, while you charge the battery, will release lithium ions. This will diffuse through the electrolyte and eventually precipitate on the other side, transferring current in this way. And we run a simulation where if the voltage is low, so there is little difference in potential from one electrode to the other, then you have this quite flat growth of the electrode. You see the change in color here. When the solution becomes dark, it means that it's getting depleted. And it's getting depleted because the lithium is trying to precipitate on the left, and it has to wait for new lithium to come from the right. But if precipitation is fast compared to the solution, this depends on the voltage, then you may have a depletion of lithium in solution. If you move to a high voltage, the depletion is even more dramatic, and this causes dendrites to grow. So this growth mechanism, and these dendrites are dangerous because they can actually reach the other electrode and cause short circuit and set your Tesla car on fire. This is a coupled chemomechanical process with diffusion, and this is known as diffusion limited aggregation. But this is something that has never been tried with the kind of model, particle-based model that I've showed you before. And finally, another area that I'm starting to cultivate now is structural topology optimization. So you get a structure and you want to find for a given set of loads and supports, what is the best geometry for the structure to resist to it using minimum material. And while this may seem a completely different world to what I've shown, actually the novelty that we are pursuing here is to represent the structures as discrete particles. So typically these methods are developed for continuum simulations, finite elements. We are developing them for discrete simulations. And if we can do that, eventually my dream would be to go back with these methods to the configurations at the micro scale and see if we can import the concept of geometry and microstructure optimization from a structural engineering point of view. And with this, I conclude my presentation. Thank you very much for listening.